The title of the work is Evaluation of Tensile Properties of FRP Composite Laminates under Varying Strain Rates and Temperatures. Here are the list of authors. Introduction. Many engineering structures in military applications such as aircraft fuselage, if explosives are carried, and in industrial applications such as high pressure vessels, may have to withstand internal blast loading in service. Traditionally, all internal blast loaded structures are covered with monolithic plates made of steel. However, steel on burst or explosion increases the risk of collateral damage by producing high velocity fragments, which may prove catastrophic in vicinity of blast site, causing fatalities or serious injuries to personnel or grave damage to structures. Reduction in collateral damage by use of lighter but not strength compromising materials for such structures is a novel concept. The fiber reinforced polymer composites and its variants like hybrids, sandwich core, and fiber metal laminates offer the best solution as they disintegrate easily on blast, thereby reducing collateral damage. The use of composites in blast applications is best known as they provide high strength to weight benefits. Blast loads typically produce very high strain rates in the range of 10 raised to 2 to 10 raised to 4 per second. This high loading rate coupled with elevated temperature would alter the dynamic mechanical properties of the structures. Under high strain tensile loading, the mechanical properties of FRP involving Young's modulus, tensile strength, tensile strain, Poisson's ratio, etc. may suffer great changes. The composite material has become more associated with FRP, where a polymeric matrix like epoxy, vinyl ester, polyurethane is reinforced with strands of fiber or a combination of fibers such as glass, carbon, aramid, etc. Therefore, the investigation of the mechanical properties of FRP composites under dynamic loadings and different temperatures is essential to design the structures with this kind of materials. The present investigation deals with the characterization of tensile behavior of various fiber reinforced polymer composites under thermomechanical loading. Five different types of unidirectional composites of carbon, glass, carbon glass hybrid, and metal laminates of carbon and glass were tested for tensile behavior. Tensile tests were performed at strain rates of 10 raised to minus 3, 10 raised to minus 2, 10 raised to minus 1 per second at room temperature, at 250 degrees Celsius and at 450 degrees Celsius. Stress strain relations reveal the strain rate and temperature sensitive behavior of composites. Glass, glass carbon, glass metal epoxy composites showed higher peak tensile stress under room temperature with varying strain rates as compared to neat carbon epoxy composites. Also, high strain rate under tensile high strain rate tensile properties such as peak stress and peak strain of glass carbon epoxy specimens were 26% and 60% higher than that of neat carbon epoxy composite. The failure mechanisms of both the composites were analyzed through scanning electron microscope. The composites mainly failed due to matrix crack within elastic range under room temperature and failed with significant plastic deformation of matrix and fibers under test temperatures of 250 degrees Celsius and 450 degrees Celsius. Methodology. Tensile test. The tensile tests were carried out as per procedure prescribed in ASTM D638. Testing was performed using a 30 kN Instron 5967 universal testing machine. The machine has a speed range of 0.001 to 1000 mm per minute and load measurement accuracy of plus or minus 0.5%. In this work, load cell of 10 kN was used for testing. The UTM was coupled with an electrical heating chamber. The chamber was set for a heating rate of 10 degrees Celsius per minute. The tests were performed at varying crosshead speeds of 0.36, 3.6 and 36 mm per minute depending on the strain rates. The test speed was controlled with strain rates of 10 raised to minus 3, 10 raised to minus 2, 10 raised to minus 1 per second at temperatures of room temperature 250 degrees Celsius and 450 degrees Celsius. A total of 9 sets of readings were obtained for each type of laminate specimen and the statistical analysis of the experimental data was done. The strain measurement was done by linear variable differential transformer with optical encoder. The heating chamber was switched on after placing the specimen in between the upper and lower grips. A settling time of 5 minutes was allowed after the chamber reaches the desired temperature. Then subsequently load was applied till fracture. The maximum load carried before failure is the ultimate failure strength of the material. Tensile test setup. The figure shows the tensile test setup. Figure A shows test machine, B shows temperature controlled chamber, and C shows specimen fixed in upper and lower grips. Conclusions. This experimental study focuses on the tensile characterization and failure pattern of 5 types of composite specimens under 3 types of strain rates and temperatures. The effects on tensile behavior and fracture morphologies are investigated and discussed comparatively. The following conclusions can be drawn from this study. The tensile strengths were significantly higher under room temperature conditions for all types of glass fiber reinforced hybrid and non-hybrid fiber composites under strain rate of 10 raised to minus 1 per second. Interestingly, all types of composites tested under elevated temperature in this study could perform better within the nonlinear region of the stress-strain response under the dynamic tensile loading for identical specimen dimensions. The peak ultimate tensile stress of GE, GCE, CME and GME composites with strain rate of 10 raised to minus 1 per second under room temperature was 75 to 86% higher than the CE composites. The elastic modulus and tensile strength reduced considerably at higher temperatures in comparison to room temperature values. The drop was reported almost 80 to 85% of the room temperature value. The hybrid combination was reported to have least value at elevated temperatures. It is reported that strain rate greatly affects the ultimate tensile strength, while temperature only influences the modulus as seen from the tensile behavior of all composite specimens. Tensile strength and maximum strain increase with increasing strain rates at room temperature, and the modulus and tensile strength decrease with increasing temperatures at strain rate of 10 raised to minus 3 per second. The SEM photomicrographs have gave clear fiber matrix failure mechanisms, which is in agreement with all the tensile test results obtained under varying strain rates and test temperatures. Thank you.